Today we are going to talk about something new, and this is lecture number 28. So far we have discussed lots of things about nanomaterials, their properties, correlation between structure, size with the properties, and we are at the fag end of this course. So what we should do now is to rather discuss you some specific special cases, and next 2 lectures I am going to do that. So before that, let me just tell you a few things. So we have discussed a lot on the properties of nanomaterials. We discussed about mechanical properties, physical, electronics, electrical, magnetic, optical properties. You must be thinking, what about acoustic properties? Well, materials do interact with radiations. We have seen in our discussions. Now, this interaction depends on the wavelength of the material, which should be comparable with the internal structure or dimensions. Therefore, in case of nanomaterials, for which the characteristic structural or even dimensional length scale is in nanometers, that is between 1 to 100 nanometers. So hence, a wide range of electromagnetic radiations will interact with the nanomaterials like UV, visible lights, X-rays, everything. But on the other hand, if you look at acoustic waves, their wavelengths are much higher, right? Their wavelength varies from microns to kilometers. So it is expected that acoustic waves will not interact much with the nanomaterials. But what is surprising is that we have discussed about uses of ultrasonic waves for the preparation of nanomaterials. What does it mean? We have shown you that sonochemical routes can be used effectively to produce different kind of nanomaterials. And this is done by using certain kind of devices like ultrasonic devices, which will produce ultrasonic waves inside a solution. And during this process, because of the interaction of the ultrasonic waves with the solution, we will have small cavities produced. These cavities are basically produced because of collapse of the bubbles. And in these cavities, you can then prepare or synthesize nanomaterials. So other than that, there is not much interactions of the acoustic waves with the nanomaterials. So hence, we have not discussed much. We are not going to discuss much about the interaction of the acoustic waves with the nanomaterials, or rather on the acoustic properties. So what then we should do in the next couple of lectures is as follows. We are going to show some specific synthesis routes and the properties of nanomaterials. And I am going to take here the examples of carbon-based nanomaterials at the beginning. Carbon-based nanomaterial means I will talk about carbon nanotubes, I will talk about graphenes, and even I will talk about some other 2D materials also in this lecture. So if I have to recap the whole thing, so we have seen that the properties of nanomaterials are affected very strongly by the size and the dimension of the nanomaterial. In case of mechanical property, we have seen the grain size of the material do affect the elastic strength or the plastic strength or even the dislocation activities, and especially we have seen the yield strength of the material scales 1 over root d, where d is the grain diameter of a nanomaterial. And this is known as a classical Hall-Page equation. But it is evident this equation also breaks down at grain size below certain value for a specific material. And that is mainly because this particular equation is based on the concept that the strengthening due to grain boundaries is basically because of the pile-up of dislocations in the grain. So, when the grain size becomes very small, this pile up of dislocations or the defects inside the grade is no longer possible, because in order to pile up the dislocations, you need to maintain a minimum distance between the two dislocations. So, hence, if I have a very small grain size, then it is no longer possible to do that, and therefore, instead of hardening effect or instead of strengthening effect by the grain boundaries, we observe softening effect, or that means we also see below a certain grain size the yield strength decreases rather instead of keep on going increasing. These are very typical features which has been observed in varieties of materials, metallic, ceramics, and we have discussed about it. And then we have discussed about a lot of things about electronic properties, how electronic structure can get modified because of size and dimensionality. We can have band structure getting modified, okay, and this will affect significantly the electronic properties, thermal properties. Okay, we have discussed a lot about thermal properties, thermal transport, right? Magnetic properties are affected strongly by the size, because the magnetic domains or domain walls, they are significantly affected by these. We have seen there is a superparamagnetic effect below a certain size. And finally, we do discuss a lot about the optical properties, right? And we have shown you very different new kinds of defects in the sense of optical properties. What is the defect we discussed about it? Do you remember that? Don't remember. So, the defects which we discussed about this is the, what is the name of the defect? Can you remember it or you don't remember it? Well, let me tell you what is the defect. The defect is known as, it is lowless. So, sometimes also instructor needs to look at the book, okay, and this is what is important, the presence of both the hole and the electrons together, okay, and this is something excitant. Yes, we have discussed about excitants for the optical properties. The excitants, their nature, how they are affected, we have discussed a lot about it. So, that is the recap. Now, we are going to discuss something new, right? Well, not something new. I have already discussed a part of it in some of the lectures. You know, carbon based nanomaterials have become very important of late, and they are very recent discoveries, maybe 20 to 30 years, yes, 30 years is the maximum. So, this whole thing is taken from the book of Michael Ashby and et al., as well as by Dieter Wohlert. I acknowledge these pictures which I have used from them. Now, if you look at carefully, these structures, what I am showing you is basically a buckyball or C60 molecules and a graphene, right. So, carbon nanotubes, they were discovered in 1991 by Sumio Iijima, you know, in Japan, and he was looking at the suits from the electrical discharge between two carbon electrodes under transmission electron microscope, and that is why he discovered. And discovery is obviously serendipity as well accidental, but you know, before him there are a lot of people who studied this about this material, mostly Harold Kroto and Richard Smalley during 1970s. Kroto and Smalley found that under the right experimental conditions, what you can have is basically carbon atoms can basically self-assemble, and they self-assembly into a molecule of specific shape, such as C61, which is shown here. You can see the C60 molecule here, this is the one, right. So, what do you see here? The carbon atoms have self-assemble under certain experimental conditions, okay, when experiments are done. And you can see there are two types of element. One is hexagonal element here, which is very routine in case of benzene rings, and also you see some element like pentagonal. Can you see that? So, let me just put a different color to make you believe that that is a pentagon. 1, 2, 3, 4 and 5, and hexagon, and you have already done that. Okay, what is that? This is the one which is hexagon. So, a combinations of hexagons and pentagons can together be used to self-assemble carbon atoms just like a ball, and this is what is called a buckyball. Okay, this name comes from structure in Great Britain. So therefore, however, Ijima has shown that under different experimental conditions, this can produce, this ball can open and then could produce a tubular structure, and that is what is known as basically it is producing a cylindrical structure. So now, as you know, the buckyballs can have different kinds of shapes, as what is shown here. This is this one, and you can also have a completely, sorry, this is this one actually, yes. Let me just, and then the new one in which you can see that other combinations are present. So now the question is, in these structures, the basic unit which is present is the graphene, it is the graphite sheet. So before I come into that picture, let me just take a few moments. Suppose if I take an hexagon, sorry, if I take a pentagon, and if I want to arrange, hexagons around it, around each of the sides of the pentagon, you will see I will leave behind certain free spaces like this. So structural arrangement will not be possible. This will lead to some kind of a voids or something. So therefore, you need a combination of hexagon and pentagons to have this kind of structures. So there are, you can see here that I am showing you two different kinds of fluorines. Okay, one with hexagons, other one is pentagons. Okay, right? This is completely with hexagon. You can see that 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? This is what it is. And this one has been two combinations of hexagon and pentagons. So now, as you can see, and this is easily available in this website, crystal.com, Stefan Weber website, and this is C60, this is C70. So 70 carbon molecules are arranged if you produce such a kind of things. It's just like a football. So the closing gap between this hexagon lead to three-dimensional structure, which is the basic thing about the fluorines, these closing gaps. So what do you understand from this picture? From this picture, you clearly understand that under certain experimental conditions, we can allow the carbon atom to shell placental and produce such kind of nice structures. And this was the discovery done long back by Harold Kroto and Smalley. They proposed this model and discovered it. Now, as far as the carbon nanotubes are concerned, because all of you must have heard about carbon nanotubes, very widely known material, and they are nanotubes, that means they are nanoscale. So in a nanotube, as I have discussed in many previous lectures, the length of the nanotube is pretty long. It may be a micron or maybe millimeter size long, but the diameter is basically in nanometric domain. They are not nano-dimensional in all the three x, y, z directions. Rather, they are nano-dimensional along x and y directions, not in the z directions. Okay. So, if you carefully look at this picture, which is taken from Michael Ashby's book, you see this is the picture of a single wall carbon nanotubes and multi-wall carbon nanotubes. So, this one is single wall carbon nanotube, is single wall CNT, and this is multi-wall CNT. What do you see here? Very clearly you see that CNTs are basically parallel arrangements of these cylinders, right? In case of multi-walls, they are parallel arrangement of cylinders. So you must be thinking how one cylinder is put inside another cylinder. Well, you may have done some experiments in your childhood where you can put one cylinder into another one. There are forces exist in case of such a kind of PCs between them. So these are produced by laser vaporizations or arc discharge or CVD, which we will discuss little later. And diameters of the order of 1 to 2 nanometers, lengths can be very long, short, and it can have defects inside it. And most of the disadvantage is that single nanotubes are very expensive, okay, because production is expensive. So multiple nanotubes are more widely used. Well, to begin with, as I said, all these structures, they are relying on the single layer of graphite. So as you know, graphite is a material in the carbon family with the lowest free energy. We have carbon, graphite, diamond, and amorphous carbon, and in fact we have now CNTs, graphene buckyballs. Out of all this material, graphite has the lowest free energy, and that's why it is more widely available in the mother nature. So graphite structure, all you know, is a layer structure. Basically it has hexagonal close packed structure. These are layers. As you see, each layer the carbon atoms are arranged in a nice manner, hexagonal manner, and between the layers there is van der Waals forces. So what one can do is simply one can take a device, one can take a knife rather and blade to chop off these layers by cutting off these van der Waals bonds here or there, and once you cut off, then you can produce the second structure, right? Although this is shown like a graphene, this is the one I have not shown you. You can see that the carbon atoms are coming like this and they are arranged very nicely. So 1, 2, 3, 4, 5, 6, right? See, I am completing it for your purpose. Similarly 1, 2, 3, 4. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 6. So you can easily generate this way, right? 1, 2, 3, 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 1, 2, 3, 4, 5, 6. Am I right? So I can generate this network. So this is the basic unit of the graphene, single layer. So now if you go back to the earlier slides, this one especially. So if you carefully look at this, this is this tube is nothing but a graphene layer wrapped around a cylinder, or wrapped into a cylinder. So if I take a singular graphene and wrapped or bent it and wrap around, I form a cylinder, right? So and then if you close the ends, you will be able to form plucky balls. Carefully, not like that, because the units here, hexagonal units or pentagonal units, both are present in the nanotubes. So what do you understand? Although graphene doesn't have any pentagonal units, these structures lead to formation of pentagonal units. That's what you clearly assume. Now CNTs are cylindrical molecules with a diameter which can vary from 1 nanometer to few nanometers, and lengths can be up to few micrometers, and their structures are consisting of graphitic shape around a cylinder. Depending on the processing conditions, CNT can be single wall or multi walls, and in particular CNTs are classified by the chiral vectors. Okay, what is that? So this is a typical structure of a graphite layer, and we go to this one, how these graphite layers are things. You can see that I can always generate two vectors, one this one, other one is this one, right? So now so unit vectors A and B and the chiral angle theta, unit vector A and B, this is A, this is B, okay, and this is the chiral angle theta, you can see here theta 0 here written, okay, and and this is the, so now the how I am going to take this vector T and wrap around, that will dictate what type of carbon nanotubes produce. So we can always take C, we can always write down C as Na plus Nb. C is a vector, right? Or Na plus Mb is better, they may not have same values, but A and B is the unit vectors, and M and N are the chiral vector numbers. The characteristic orientation of hexagon in a corresponding graphene sits. Okay, you can clearly see that is why the characteristic orientation of the graphene things. Okay, so now in this configuration, the value of the chiral vector C is the circumference of the nanotube, and the direction related to the unit vector A is this chiral angle theta 0. C is at an angle theta 0 respect to the unit vector A. The translational vector T is basically telling us the nanotube length, which is thus perpendicular to the C. So, these parameters describe the way in which the graphite sheets can be rolled up to form this nanotube structure. In a regard, three types of nanotubes can be produced. One is armchair, zigzag, and the chiral. Right? Three types of nanotubes can be produced. So, depending on how you are going to do that, the zigzag forms when m is equal to 0. What is m? This is the m. So, that means zigzag forms when B vector has no importance, it is not used, only A is used, right. And so, armchair machine is formed when n is equal to m. So, armchair is forming when n is equal to m, and zigzag forms when m is equal to 0. Oops, this always happens. And chiral is what when we are doing rotating around this at an angle with that. So, this is how we can generate three different types of nanotubes. So, that is very important, how nanotubes are formed very clearly. The chiral occurs when the chiral vector numbers can be assumed any integer values, and the chiral angle is intermediate between 0 and 30. So, what is the meaning of this? The chiral vector numbers, that is n and m, can be any integers. They need not be 0 and need not be equal to each other, but they can be any integers, and the angle will be between 30 and 0. Among these three different types of constituencies, among these basically singular nanotubes, there are metals though with n minus equal to k, k is the integer. And these ones are actually semiconductors with a small band gap, and remainders are semiconductors with the band gap that is inversely proportional to CNT diameters. So, as you know, CNTs can be prepared many ways. Best to prepare CNT is basically arc discharge method. So, in this method, this is taken from Dieter Verlag's book. In this method, arc actually causes the graphite to melt. So, you can have two graphites and you can produce an arc between them, and this arc will cause the graphite to melt. Outside the droplets, whatever melt droplets form, they cool very fast rate, and this can lead to glassy particles. Liquid inside these droplets can cool slowly, and it can become supercooled, and later on can crystallize as nanotubes, dragging out some liquid droplets, liquid carbon dioxide droplets. So, carbon nanotubes produced basically by this arc discharge method. You can also produce by, as I discussed in some slide back, by laser vaporization also. Again, laser is used as a high energy source to melt, and when you melt, some of the droplets will be undercooled heavily, and that is why they can produce nanotubes. You can also produce by some other routes, like what? Like this. Okay. This is the things which we will discuss a little bit more details, and this is something which is widely used in the literature or in the experiments. What is that? How this is produced? Okay. So, synthesis, this is basically produced in a tabular furnace or tubular furnace. The way this is done is as follows, correct? If you in electric direct current or the surface of the electrodes, carbon is, as we said, known to melt. Subsequently, temperature will drop, liquid carbon becomes supercooled and begins to crystallize. Crystallization nanotube grows through the liquid layer at the cathode. That is what is shown in this case. The nanotubes will go, you can see that these droplets, they have joined, and these are actually nanotubes, okay, which has formed because of the undercooled liquid droplets. Yield of the nanotube significantly can be improved by metallic catalyst to the carbon electrodes. However, in order to obtain large amounts of nanotubes, more sophisticated processes has to be used, and most common one is a tubular furnace, which is shown in this picture. and it is heated up to 1300 Kelvin, that is approximately about 1000 degrees Celsius, at which carbon nanotubes are obtained at the presence of catalyst. Arc discharge leads to very small production of the nanotube, that is why this method has come. For carbon nanotubes, a mixture of methane gas and hydrogen is basically allowed to enter into this furnace, and which is basically diluted, can be diluted by argon. As a catalyst, we can use iron, nickel, or even alloy of that. And these catalysts, are basically used to start the formation of the nanotubes inside these furnace. So you have to maintain a critical temperature in the furnace, which is about 1300 Kelvin, and you have to use some metallic catalyst. Okay, that's how this can forms. So how this is done? So these are the nanotubes produced in the tubular furnace. You can see here methane was used as a carbon precursor. This is taken from the permission with Hampel and Leonhard, which are basically available in this book of Dieter Verlath, and I acknowledge their contribution. And here iron was used as a catalyst, and temperature was used taken 1300 Kelvin. So let's look at a little bit about details of that, how this catalyst can help growth of the nanotubes. Okay, a typical product obtained such space is basically ball of wool, as you have seen in this last picture. Okay, and this is a typical example of carbon nanotubes product insert from the methane. So instead of using randomly placed catalyst particle, it is possible to prepare clear-cut patterns of the carbon catalyst particles either by printing or vapor depositions, and so this catalyst basically start absorbing carbon, and the carbon will basically get dissolved inside the metal, because most of the metal has ability to dissolve carbon. When more amount of carbon is dissolved in the metallic catalyst, then they started coming out as carbon nanotubes. That is what is being observed in most of the cases. So this is one such picture. You can see the frozen nickel doublets, which was used as a catalyst and seen at the end of the carbon nanotubes. The electron diffraction pattern also shows the hexagon structure of the graphene sheet, which is very clear. So these catalysts can basically allow us to produce large quantity of the this kind of nanotubes. That is what is the major means to produce the nanotubes. So let us now discuss a bit about the graphene production routes, then we will talk about applications. So graphene is a more much recent discovery. It was discovered by Novoselov and Green in UK, and then awarded Nobel Prize in 2004. So the first technique which is widely used is basically known as a Scotch tape technique. This is nothing but mechanical exfoliations. So now before I discuss about this exfoliation techniques, let me go back to the structure of the graphite. As I said, we can always use a blade or a knife to cut off these intermediate bonds and produce this single layer of carbon, right? This is a dream for the human for a long time, but it was only realized when in the beginning of this century, something around 2002 or 3, this was realized. So how it is possible? It is easily possible to create all kinds of structures by using graphene sheet, as we have discussed. So graphene is the basic thing. As you can clearly see how by rolling of graphene sheet can lead to 0-dimensional buckyballs or 1-dimensional nanotubes, or even stack of these layers can lead to 3-dimensional graphite. Okay, so buckyballs were discovered in 1986, nanotubes were discovered in 1991, and graphite was discovered long back in 1500. Graphite is a naturally level material, and this is the paper by Grimm and Novoselov in Nature Materials, which is widely respected. So now the question is this: how we produce that? So this is this picture is taken from the paper by Li and Chen, Journal of Material Chemistry. As you can see here, what is done is very simple. You take a double-sided tip, and then you put this graphite within the tip. Just basically put the graphite and then close the double-sided tip. Then slowly peel off this tip. If you peel off you will basically produce different material on the scotch tape itself. And then if you use a knife or something to scrub the material which is basically attached to this tape, what you will see is there are these layers of graphite present. But only when you look at very closely, that is what is done by Graham and Mosolov, you will find they are actually thin layers of graphene. Now, how do you confirm that? We can easily confirm by using an optical microscope. That is what I always tell to young students, that doing experimentations of this order does not require you to use very costly equipments. So, you can take these thin layers which are there on the scotch tube and put it on a glass slide, and then you just put it on an optical microscope. Okay? And then if you see that these layers are transmitting most of the light, then you are 100% sure the single layer of graphene, because if a single layer of graphene, it will not absorb any light. Only when its stacked layers are present like in graphite, it becomes opaque to light. So, that is how it is discovered. So, this is known as a mechanical exfoliation. Now, we can also use technique like chemical exfoliation. What is that? Well, most easiest one which you may have heard is the Hamas or modified Hamas methods. This particular picture is taken from Parvez et al. So, you have to understand I am using different literature which is available in the internet, because these things are not available in a book form, or even if it is available, scattered information is available. So, that is why I have to use such a kind of literature. I acknowledge this literature for use for this kind of lectures. So, what is done here? You can take a graphite and then you can basically put a graphite in a mixture of hydrochloric and nitric acid. It will be boiled in that acidic medium. So, if it boils, then graphite will exfoliate. That means the layers of graphite will open up, but at the same time it will get oxidized. So, once it gets oxidized, you will get graphitic oxides, or what is known as a GU popularly. Then you can use some reducing agents to reduce graphitic oxide, or what is called RGO. That is basically not exactly graphene, but maybe several layers of graphite are present. We can also do, this is the simple one which is used, what is known as oxidative exfoliations, which is easy to do in the lab and experiments. Second one, what you can do is you can do electrochemical exfoliations, where you can basically use electrochemical cell. You can use a platinum and graphite electrodes and a electrolyte, and then you can apply a huge current to it. So, what will happen is that because of application of current, and here from the graphite, the things will get removed atom by atom or layer by layer and get deposited on the platinum electrode. Okay, it is used as a cathode and graphite is used as an anode. So, graphitic material will get removed from that and then deposited on the layers of the platinum. So, then if you scratch on the platinum, what you can get is a graphene layer. Okay. Or what you can do is you can use liquid phase exfoliations. What is that? This has also been discovered some time back. You can use basically a grinder mixture. What is we used in the kitchen blenders or kitchen grinder mixtures can be used. In kitchen blender, kitchen grinder mixture, we can have liquids, certain kind of liquids, and you can put this graphite in that. These liquids are basically used to reduce the surface energy, the interfacial bonds energies between the layers of the graphite. Then you can use shear flow. So, once you have a liquid, and if you use in a jar of mixer jar, or basically then you have to have, and blades will move at a very high speed, and because of that a turbulent flow is created, and this flow then can allow this layer to be removed one by one. I can produce graphene. In fact, this is the technique in which you can produce large quantity graphene, and this is now widely used to prepare large quantity graphene. In fact, it is available in the market also, you can buy that. So, this is how the chemical exfoliation techniques works. So, compared to physical exfoliation technique, chemical exfoliation technique is more versatile, and it can lead to large scale production of the graphene also, which is very important for any applications. Now, the last technique which is I will talk about the production is the chemical vapor deposition, or is known as CVD. CVD is is basically thin film deposition technique. So, here also we can use catalysts like nickel. So, what is done is basically take a nickel plate, heated up to certain temperatures, and then you can use mixture of basically you can use methane gas, and once the methane gas is dissociated at high temperature, and it will produce carbon, and byproduct is as a gas, which is mostly basically moisture, and this carbon then can dissolve inside the nickel, and then once nickel is supersaturated, again nanotubes on the form on the surface of the nickel. So sorry, graphene will form on the surface of the nickel. This is taken from K.M.L. Surman. Is basically there's a conference in 2014 on COMSOL, and this particular picture was depicted there. So that means we can produce graphene by physical exfoliation, chemical exfoliations, or by chemical vapor depositions. So now we'll talk about in the next 5-6 minutes or so, we'll talk about how we can use CNTs and graphene. So this is for the CNTs. CNTs can be used for typical field effect transistors, or you can use for hydrogen gas storage, or you can use, we must have heard about that, you can use as supercapacitors. Okay. So let us talk a little bit about it. Field effect transistor is basically a type of transistor used for weak signal amplifications, and they are currently made from silicon. Silicon is widely used material, that's why this is it. However, these devices are still a few 100 nanometer in size. The use of CNTs with size less than 1 nanometers in diameter would allow more of these switches to be part of this chip. So in effect, the current flows to a CNT. Okay, you can see there's a CNT layers kept here. Current flows to a CNT with the semiconductor pattern properties along the path called channel. Okay, you can see there's a channel like that. One side of the channel is a gold electrode called source. Other side there is a drain, okay, right. So with a small voltage to apply to the silicon substrate, which can act as a gate in effect, the conductivity of CNT can change by more than million times. So it can then allow us to amplify the signal, which is very common. Another application of CNT is in fuel cells or batteries, okay, and both in case of storage of purposes. So in case of fuel cell, CNTs can be used as a storage of hydrogen, particularly for the automotive applications. Okay, and it can basically take about 6.58% of the hydrogen. Ratio of hydrogen to hydrogen storage, material is about 6.5%. That is 0.065, which is not bad, but not very good also. So hydrogen level can be achieved. Higher hydrogen level can be achieved by gaseous and liquid hydrogen, which is hydrogen can stored in the cages of this graphitic network. Okay, you can also use these CNTs for other purposes like, as we said, supercapacitors. Okay, so what is that? The supercapacitors are basically what? This is because CNTs exist high porosity, a large specific area, high electrical conductivity and chemical stability as compared to other materials. In a conventional capacitor, energy is typically stored by transfer of electrons from one metal electrode to another metal electrode separated by electronically insulated material. The capacitance will depend on the separation distance between these and the dielectric constants between these electrodes. In case of supercapacitor, there is instead of electrical double layer. So you can see that there is electrical double layer created between these two things, and each layer contains highly porous electrodes supported by another electrode. Applied potential on the positive electrodes attracts the negative ions in the electrolyte, wherein potential on the negative electrode attracts the positive ions. The dielectric material between these two electrodes prevent the charges from crossing between the two electrodes. If the electrodes are made of CNTs, effective charge separation is about few nanometers compared to separations of the order of micrometers in ordinary capacitors. So hence they are called supercapacitors. You can also use this for other purposes like flat panel display, or you can use in fact CNTs as emitters. CNTs can use as for high value of emitters, like in case of electron microscopes where you need large electrons come up. So, you can see if depending on the closed or open loop, you can have different amounts of currents, emission currents produced 10 to the power minus 3 to 10 to the minus 7, so 10 to the minus 7 to the power 8 amperes can be produced depending on that. Electron emission is closed and open loops is open nanotubes are compared. Well, field emission current of current nanotubes basically depends on the bundle of nanotubes embedded in a matrix of electrically non-conductive polymers. So, you can see the range of fluctuations are present for certain values of voltage, and high value of voltage this become very stable. That is what is the another use of CNTs. CNTs also can be used for flat panel display. Okay, we all know the flat panel TVs or flat panel display now. So, we can use CNTs as on the elements of the flat panel display, which is now widely utilized. So, what about graphenes? Graphene can be used again for many various applications, including energy storage, transistor, or even waveguides. Okay, and these are all taken from the book from the paper by Chuang et al. In Frontier Physics very recently. And energy storage is obviously they can be used for various kinds of storage like supercapacitors also they can be used, and they can also use as a transistor. Okay, in a transistor basically as a layer between two electrodes because they have high electrical conductivity. They can also be used as waveguides because they have unique optical properties because of the localization of the optical waves. It can be used for waveguides. So, with this let me also talk about some other 2D materials. As you know, there are many other 2D materials which have come recently, and they are very famous in fact, as famous as what? Graphene or carbon nanotubes. Okay. So, let us talk a little bit about those also, then we can wind up this lecture. As you know, long back Tenney et al. Has reported that this is from the US sorry, the all compounds which are crystallized in layer structure can be used to form nanotubes or fluorines like structures. And first nanotube consisting of without any carbon material is MOS2 and WS2. Which are typically known as a MOS2 and WS2. But structures were laser observed with selenides of molybdenum and tungsten also. The important thing is that each layer structure is like this, X, Me, X, where X is the sulfur or seleniate and M is the metal, and this is repeated. So, within each triple package of layers there is a covalent bonding. Within there is a covalent bonding. When outside this triple package there is this van der Waals bonds. Hence, package can be shifted against each other, and this is the reason why MOS2 and WS2 are like graphite, and the technical basis technically they are used as lubricants. Similarly, recently we have also seen boron nitride, okay, BN. Boron nitride. But boron nitrides they have no free electrons, so therefore they are insulators. So, you can produce 2D insulators also. Okay. So, you can see here multiple fluorine particles of MOS2 also can be produced. Here many layers of this MOS2 has been come together or self assembled and produced. You can also have MOS2 layers. This is taken from our own work. MOS2 2D, you can see they are transparent to electrons, very thin. They are produced by sonochemical techniques. So, in a nutshell, what I discussed today is that about CNTs and graphenes and some other 2D materials, their processing routes and some of the applications. I thought this is important for nanomaterials, so they should know about it. The next lecture, this is lecture number 29, we are going to talk about polymer nanocomposites. So, that is the lecture number 29, and that should wind up our course. Thank you.